Imagine wanting to create stunning, realistic images from scratch, like a blank canvas. Today, we're exploring a powerful class of generative AI that achieves exactly this: diffusion models.
We've seen generative models before, like GANs in VAEs, but are diffusion models doing something fundamentally different to get such impressive results?
They are. The specific family we're focusing on are called Denoising Diffusion Probabilistic Models, or DDPMs. This paper, from Ho et al. In 2020, really brought them into the spotlight for image generation.
Denoising sounds like removing noise, but why would we add noise if the goal is to create something pristine?
That's the core question. These models are fundamentally statistical physics inspired. They see image generation as reversing a thermodynamic process where things inevitably move from order to disorder.
So they model the gradual breakdown of an image into noise, and then they learn how to reverse that precise process? It's like learning to unscramble an egg?
Precisely. The paper highlights a novel connection between their approach and denoising score matching with Langevin dynamics. It's about finding the gradient of the data's probability distribution to guide the denoising.
Langevin dynamics. We've heard that term in other contexts, often associated with sampling from complex distributions, right?
Yes, it's a powerful sampling technique. For diffusion models, this means they naturally admit a progressive, lossy decompression scheme. You can think of it as gradually restoring detail, step by step.
So it starts with total noise and then slowly refines it into a clear image, adding more and more information?
Exactly. And the results were state-of-the-art. For example, on a dataset like SciFar 10, they achieved an inception score of 9.46, indicating high quality and diversity in generated images.
That's a strong benchmark score. It tells us these models are generating images that are both realistic and varied, not just copies.
Indeed. They even achieved sample quality similar to progressive GAN on 256 by 256 LSUN images. Progressive GANs were a leading generative model, so this was a significant statement.
So DDPMs were competitive with, or even surpassed the previous best. That's a huge claim for a new generative paradigm.
It was. Now that we understand what DDPMs achieve, let's trace the intuition behind how they actually work. We'll start with how they add noise in a controlled way.
Lillian Wang's blog post is fantastic for building intuition. She confirms that diffusion models are inspired by non-equilibrium thermodynamics, echoing what we saw in the DDPM paper.
So it's like a scientific process where a system naturally moves towards a state of higher entropy or disorder over time.
Exactly. They formally define a Markov chain of diffusion steps to slowly add random noise to data. Each step is small and depends only on the previous step, like a sequence of gentle blurs.
A Markov chain means each noisy version of the image only depends on the one just before it, not the whole history. That simplifies things.
Consider an image, x0. We apply a little noise to get x1, then a little more to x1 to get x2, and so on, producing a sequence of noisy samples x1 ... xt.
So x0 is the original image, and xt is basically just pure Gaussian noise with nothing recognizable left of the original?
That's exactly right. As the article states, eventually when t approaches infinity, x sub t is equivalent to an isotropic Gaussian distribution. The image is totally obscured.
So the forward process is fixed, we don't learn it. We just apply Gaussian noise iteratively.
Yes, it's a defined process. A useful property is that we can sample xit at any arbitrary time step t in a closed form, using the reparameterization trick. This means we don't need to run the whole chain.
That's smart. If you wanted a slightly noisy image, you don't have to start from scratch every time. You can just calculate it directly.
Now for the magic, the reverse diffusion process. If we can learn to accurately predict and subtract the noise at each step, starting from pure Gaussian noise, we can generate a new image.
This is where the learning comes in. The model has to figure out how to unnoise the image, effectively going from blur to shark.
Here's the challenge. The true reverse process, sampling from Q of xt minus 1 given xt, is intractable. As the text says, we cannot easily estimate this because it needs to use the entire dataset.
So we can't directly reverse the exact noise function. We have to learn an approximation of it.
Exactly. This approximation is where the neural network comes in, and it's what makes the system powerful. Let's look at how that learning process actually works.
Since the true reverse step is intractable, we need to learn a model p theta to approximate these conditional probabilities. This p theta is typically a neural network trained to predict the noise.
So the neural network is essentially learning to reverse the noise addition process step by step for all those t steps.
It's structured as a latent variable model, and the article points out this setup is very similar to VAE, and thus we can use the variational lower bound to optimize it. That's a familiar pattern for generative models.
Ah, the elbow. So it's maximizing the likelihood of the data by optimizing a lower bound, just like VAEs do, even though the architecture is different.
The key insight for training is that instead of directly predicting the mean and variance of the previous state, we can reparameterize the Gaussian noise term instead to make it predict epsilon t.
So the network isn't learning a complex distribution. It's just learning to predict the specific noise that was added at that particular step.
Exactly. Given a noisy image xt at time step t, the neural network learns to predict the noise epsilon t that was added to get to xt from the clean image.
And once it predicts the noise, it can subtract it to get a slightly cleaner version and repeat the process.
Interestingly, Ho et al. 2020 found that training the diffusion model works better with a simplified objective. They simplified the complex variational lower bound.
So sometimes focusing on the simplest, most direct task for the network is more effective than a theoretically more complex one?
Yes. The final simple objective is to minimize the mean squared error between the predicted noise and the actual noise added. This directly trains the network to be a good noise predictor.
That's elegant in its simplicity. Predict the noise, subtract it. It makes sense why they called them denoising diffusion probabilistic models.
This denoising objective has a deep connection with noise condition score networks, NCSN. Those models also learn to estimate the score, or gradient, of the data distribution, which is closely related to predicting noise. So DDPMs found an elegant way to achieve similar goals to other score-based generative models, but with this clever reparameterization and simplified loss. They did! DDPMs generate high-quality images, but they have a limitation that next-generation models like latent diffusion models address. Let's see how. The main challenge with original diffusion models is that they typically operate directly in pixel space. This means optimization of powerful DMs often consumes hundreds of GPU days.
Hundreds of GPU days just to train a model? That's an enormous computational cost, making high-resolution generation practically impossible for most.
Precisely. This paper, High-Resolution Image Synthesis with Latent Diffusion Models, addresses that. Their goal was to enable DM training on limited computational resources while keeping quality high.
So, how do they reduce the computational burden without sacrificing the incredible quality that diffusion models are known for?
They introduced the core idea of latent diffusion models, or LDMs. Apply them in the latent space of powerful pre-trained autoencoders. Instead of pixels, the diffusion happens on a compressed representation.
An autoencoder, so the image is compressed into a smaller abstract representation, then diffusion happens there, and finally it's decompressed back into an image?
That's exactly right. This allows for complexity reduction and detail preservation. The autoencoder handles the high-frequency details, freeing the diffusion model to work on the more semantic parts.
This reminds me of the bottleneck concept we discussed in natural language autoencoders, where compression forces the model to learn meaningful representations.
A crucial architectural addition is introducing cross-attention layers into the model architecture. This allows LDMs to be conditioned by various inputs, like text, greatly enhancing their flexibility.
Cross-attention. So the model can now pay attention to external information, guiding the image generation beyond just denoising?
Precisely. This combination makes high-resolution synthesis possible in a convolutional manner, enabling the creation of larger, more detailed images that were previously out of reach for diffusion models.
So we get the quality of diffusion models, the efficiency of latent space operations, and the steerability of attention for powerful applications.
They truly do. As the abstract states, our latent diffusion models, LDMs, achieve a new state-of-the-art for image inpainting and highly competitive performance on various tasks.
Image inpainting, unconditional generation. It shows how versatile and robust this latent space approach makes diffusion models.
LDMs significantly reducing computational requirements compared to pixel-based DMs makes them practical. This idea is now a fundamental building block for many of today's leading generative AI systems.
I'm Maya. Thank you for thinking this through with us.
I'm Arjun. Another idea in 3 hours. Take care of your mind.